Hi. Hi. So good afternoon, and thank you so much for the enthusiasm that you bring. So today we are having this one of our. So we wanted to do more and more serious outreach, and we realized that we need to show you something that you don't expect in everyday world. So that is effort in that direction. So I have two faculty members. One is Anand Jha, raise your hand, and Aditya, and both of them are in the physics department, and they indulge in everything fantastic. All right, so I will not talk about the research, but essentially I want to welcome you to the quantum world. And by the way, the quantum is not so esoteric; it is there in everyday life. So let me just give you. I take 2 minutes. Aditya is the name. So sun is the source of all our energy, as you know. And you know, plants do it, they are the most efficient. If you look at a textbook in undergraduate curriculum, they'll tell you chlorophyll making this, that, light to sugar efficiency is 30%. Right? That's a number that hides a lot of detail. So let me just tell you that there are 30 and odd steps to be done. If 95% accuracy happens for each step, then it turns out to be 30% accurate for the whole thing. So you can clearly see that every step is 95 and above percent accurate of going from, from point number 1 to point number 2 and so on and so forth. The other amazing part is if you just look at the flux of number of photons that come in from the sky, it's about 10 over 20, 10 over 21. Please calculate, figure it out, and you'll see that's the number of photons that come in. And now one can ask, what is the number density of chlorophyll molecules in these, right? And bingo, the number is 10 power 20. So literally every photon makes sense. Nature is not crazy. Left to itself doesn't just make so many bees. It is not so many bees. It is trying to extract every photon that is coming and make it useful. Okay? So the foliage that you see is not by accident. It is to utilize every photon there. So almost at the very basic of life, it is the quantum that works. If you are looking at few numbers being very efficient to do few things, right? So every molecule looking for that photon. Remember, clouds come in, wind blows, shadows come in, this and that, and all that it wants to account. So you have larger number density of beams so that you can extract every photon. So quantum is everywhere. This is sort of an in-your-face experiment that the two of my colleagues will show. And let me first thank the team. So these guys, they're in the lab of Anand largely, and these guys have actually stopped working for last 10 days. Is that correct? Just to set up this thing appropriately, properly. Right? So Suman, stand up. Yeah, thank you. So Suman is the senior student who set it up. Radhika, please do. Yeah. Then Pranay.
Yeah, this side.
Yeah, this side. Yeah, okay. Nilakshi and Harshal. Yes. So thank you very much, guys, for getting it all together, and yeah, enjoy the talk. Oh yeah, of course I need to welcome the Christchurch College students who have been very patient and absolutely amazing. They have been sitting here quietly for more than half an hour. Right? Thank you so much, and welcome to the campus, and thank you to the faculty from Christchurch. Thanks. Welcome.
Right. So good afternoon, and very sorry first of all that we made you come here Sunday afternoon, 3:30 p.m. For our own students, we understand how difficult it is to move out of the hostels on a Sunday afternoon. But we are extremely glad and happy that most of you, have come here without foundation. So it's not like this is a makeup class or this is a compulsory attendance thing, but out of your pure interest, you have joined us. And we hope that by the time this ends, you will feel motivated and excited enough to demand that this should become a regular activity. Okay, so let's start with the show today. And as Adit has very aptly titled it, When Quantum World Comes Alive. Now again, if we talk a bit more technically, for example, MSc students and BS students who have taken a couple of courses on quantum mechanics, quantum world is not coming alive, it's all throughout. Right? The world is made of, world is quantum. This is the nature of things. Right? So, but as an outreach, this title seems quite nice. So, what we are going to do is, or rather what we have planned is, and again, the planning has been done by Professor Anand Jha and his team. I am here because I wanted my course students to see this. Right? So basically, I sort of keep pestering them. You know, you do it, you also call your students, we'll call our students, but let them show this. Right? So, three main things: quantum indistinguishability, quantum erasure. So this is a concept which we want to demonstrate, and most of us are aware of this concept, but I'm sure very few of us have gotten the chance to actually see this experimentally. Right? Then of course the wave, it's a wave particle duality. Of course an article can be a particle, so it's okay. So wave particle duality, which we learn as a principle, we always get a definition which tell you there is this behavior and that behavior. However, there is no duality here. This is again how things behave. This is how nature works. We perceive it because classically, intuitively, we have differentiated between wave nature and particle nature, and for the lack of more evolved vocabulary, we call this as wave particle duality. But there is no duality here. It's just how the things are. Right? And the third one is single photon interference. And that is the most high-end thing that you will sort of ever encounter, even if you continue in academics, in research field. The two tables that you see there, the breadboards, optical breadboards, are altogether 50 lakhs. Altogether, that's worth 50 lakhs. Right? So this is something that every student of science has to experience, and that's the goal of today's show. Okay, and let me continue calling it the show. Okay, so let's start with a sort of fun animation thing, and then we'll get to this more serious business. Quantum indistinguishability, we all have learned it in terms of interference, like the interference phenomena. Most of us have again learned it in our undergraduate, intermediate, postgraduate classes as interference of light. Now, of course, that's true, and that's the easiest one to demonstrate, to see in nature. And then you realize that, okay, fine, interference is not really only particular to light beams or photons. Electrons also show this, neutrons will show it. In fact, any particle in nature will show interference behavior depending on certain constraints. So this is what we want to show. And again, the idea is to show this through part difference or phase difference. Now what we are going to do is, we are going to reduce this through a new type of interferometer, new in the sense that this is not part of a regular coursework. Although the interferometer was designed in 1890, so nothing is new there. Right? So it's called Mach-Zehnder interferometer. And
just click on the slide.
Okay, so the pointer, but let me just go here. So it's Mach-Zehnder interferometer, which was designed in 1891-92. Around that period. Now, why that date, why that year is important, or why we need to sort of also always associate that, okay, fine, there's something which was in 1800s or late 1800s, is because what it tells us is whoever designed it and explained the working and observed the phenomena, there was no quantum aspect. Right? Quantum theory was proposed, black body radiation in 1900. Then 1905, and the formal, sort of the old classical quantum theory from Planck came in 1910. However, interference was known, let's say 200 years before, and Mach-Zehnder interferometer was subsequently developed in 1890, right? So that means whatever we are seeing had a classical explanation. Quantum interference phenomena has a very nice classical explanation. All waves show interference, superposition of wavefronts, right? So it can be explained. However, this is also an excellent tool to demonstrate indistinguishability of identical particles, and those could again be photons or electrons or any other quantum particle. Right? So, in very brief, this is the setup. So this is exactly the setup that we'll later on show you on one of these optical breadboards. The main components are, we have two beam splitters, and an optical beam splitter is nothing but a device which separates out the beam into orthogonal directions. Right? So that means once a light beam enters this, there is a probability that it will go in one direction and in other direction. If it's a balanced beam splitter, it will sort of divide this light in classical terms into half. So 50% of intensity goes in one direction, 50% in the orthogonal direction. And then we have two paths. So the light going up reflects back from this now normal mirror, goes in this direction. The light going straight reflects upward from this mirror, goes in another beam splitter. So we recombine this and we see the output. Now again, from the second beam splitter, the output could be in two different directions. You put two detectors, you can look at which way the light is coming out. And classically, again, what you expect is light divides two ways here, should divide two ways there, right? And I can do a classical probability calculation and find out the and find what should be the intensity in my two detectors. Okay. However, in terms of photon, if I want to explain the same thing in terms of photon, all it's an electron, right? Where we associate a probability amplitude, and then square of that is the probability. So the green man is my photon, a single photon, right? Which I force to go towards my beam splitter. Right. Now when it enters the beam splitter, it starts to think because it has two ways to go. Now which way I should go? It's a single photon. It cannot divide into half. So when we say a photon or the probability amplitude divides, in terms of photon, it's characterized by energy. It has energy h nu. Although, if I send a laser beam, half of intensity will go in one direction, other half in another direction for a balanced beam splitter. The photons still go either in one direction or the other. So the h nu does not get divided to h nu by 2. It's a probability amplitude, right? So that means the photon has to take a call. Statistically, half the photons will go in one direction, another half in another direction. However, for a single photon, it's a call that it needs to take, it needs to decide which way to go. So it decides that, okay, fine, I'll go here, I'll go there. So the probability amplitude gets divided. It travels in both the directions, and then it reflects from the mirror, comes at the second beam splitter, and now again you have a choice which way to go. Now what is observed, what has been observed for past 140 years or 150 years about, right, since 1890, is that the photons, when they recombine, they do come out in only one direction. So if the initial photon comes out from one direction, if you recombine it at the identical beam splitter, it again comes out in the same direction. Somehow it knows, even after getting divided twice, it knows what was my initial state. Of course, we will explain this in terms of interference and proper superposition of wavefronts and all. What one can also do is one can try to measure, and that's a measurement problem, that you can try to measure which path the photon is taking. Now, how do you make a measurement? Just like D1 and D2 are detectors, which measure the intensity of number of photons or the light beam, I can also decide that let me see which path the photon takes. One of the simplest ways would be to block one of the paths. You put a brick wall, so the photon cannot pass through it. If it cannot pass through it, that means whatever light comes from the second beam splitter is coming from the upper path, right? And now if I do the experiment, I will perform the same thing. Let my photon go through. At beam splitter 1, it has to make a choice, right? So it makes that choice, goes on. The first path is blocked, second path is still there. So it goes there, and it again has to make a choice. Every time you encounter a beam splitter, you have to make a choice which way to go. And now, its choice is easy. Because it's coming, it has only two paths to go. Half the time will go in one direction, half the time will go in another direction. Right? So just the mere fact that now there is only one path makes it act identical to what it was doing there. However, when it has two paths that we saw earlier, in this case, when it had two identical paths to follow, right? And we are not making a measurement, so we are not finding out which path the photon is taking. In that case, you do see something called an interference, right? So this is a Mark-Zehnder interferometer. For the 431 strength, we already discussed in detail in our last lecture, and now the story starts. The show starts from here. That can we actually see this? When we see this, do we understand that interference? And at some point of time, when all of you will ask you, and when most of you will claim that yes, you are understanding what the interference is, you do understand what is the phase matching, you can explain which way the fringe, which way the pattern would look, how the pattern will change. We will ask you something which most likely will then blow your minds off.
So, thanks to Professor Aditya and Professor Kelkar for the nice introduction and arranging everything. And thanks to Aditya for very nice fun introduction. Now we go a little bit more technical and do the experiments as well. Well, I'm Anand Jha from physics. So again, this is supposed to be very interactive. So anybody has any question at any point, please do ask. And that way, sometimes it's much better to kind of convey the idea. We will be showing you the setup that we have to quite some extent. If few of you want to see it, maybe at the end we can let you have a peek. But as we said, 50 lakh worth of equipment. So I do want to keep a distance. But maybe few students, if you want to take a peek at the end, that should be fine. Maybe one by one. So again, any question, just shoot any time, because that is the whole point. Questioning is makes it much easier. Okay, so these are three things we are kind of covering today: indistinguishability, ray particle duality, single photon interference. And now we'll go one by one. So Aditya's version was the human photons. We will do now the real actual photon. And how do you get the photon? That's again is a very difficult question, but typically if you have a laser, for example, what I'm holding in my hand, this is also kind of like a laser. So you have a laser, what we have is what's called a helium neon laser, that's what I'm getting here. So it can give me light at the level that you can actually see. But it can, if I attenuate, that means that if I put filters so that distinguishes the light, reduces the intensity to such an extent that I have only one photon coming at a time. That means I have only h bar omega energy, whatever is the frequency of that laser, that much energy coming out. But right now, let's take a look at this at the level where you have a beam. You can see this is a beam of light coming. So that's what we have. So this beam of light comes, hits this beam splitter. You have to make a choice. The beam has to make a choice. And this you might have seen if you have in physics optics courses. Of course, you can guess this beam splitter means it has a split half and half. So half the beam goes this way, half the beam goes this way. And then they combine here, and then at this camera, you see interference. Now, why do you see interference? Is because of this. Because although they go exactly parallel, but it is very difficult to do. So there's always some angle between this beam and the one that is getting reflected back like this. So there's some angle always, and as a result of this angle, you actually will see an interference pattern. This is the very same interference pattern that you see in Young's double slit experiment if you have done it. You have one beam of light, another one, and then little bit, and then you see the interference. If you change the slit separation, that changes the slit, that changes the separation between the fringes. We'll show you Young's double slit as well. So if these because the angle between these, you will actually see interference. So this is what happens. This is what you are probably familiar with at the high light level, that the light field comes in, splits into half. This means we are dividing the amplitude of the field that is coming here. It also means, at least classically, for wave theory device, that we are also dividing the energy. Right? If you have 5 milliwatt of beam coming in, 2.5 milliwatt goes this way, 2.5 milliwatt goes this way. Very simple. So division of amplitude essentially implies division of energy in the classical form. But now we come to quantum. So I now am attenuating the intensity laser so much that I have only one photon. That means h bar omega worth of energy coming out from this laser at any given time. So now when this comes, reaches the detector, so the beam splitter, and again, as Aditya was saying, it has to make a choice. Now, what choice it has? It cannot divide itself. So it has to make a choice with the constraint that it cannot divide itself because photon energy cannot be divided. That is the concept of photon. That is the starting point of quantum mechanics. So it cannot divide its energy. So what can it divide? We don't know. But let's see. So, but if it has to reach this camera, the detector, it has two ways. One, it can go like that to the camera, or it can go like that to the camera. It simply cannot do it. That's a huge constraint we have. Classically, half goes this way, half goes this perfectly fine. But quantum mechanically, this we want to show you again and again. Quantum mechanically, it can either go like this or go like that. So if a photon goes like this or goes like that, then what interferes with what? That is a question that we will try to answer. But this is how this is what the constraint that a single photon has to follow, that it cannot divide itself. It doesn't have that luxury. So just like we have the classical word in the wave word that if we divide the amplitude, that means dividing the energy. But for photon, you cannot divide the energy. So what do you divide? What happens? That is the quantum theory. That is precisely the basis of it, and we'll show you the consequences of that. Okay, so now how do you explain how the interference happens, if at all? Then the thing is that the photon has two possible paths, right? This or that. The theory says if the photon paths are indistinguishable, that means the photon goes this way and the photon goes that way. Now, from the detector's perspective, if there is no way, if you have no way of telling whether the photon came this way or came that way, means you have a detector, you will detect the photon, and the photon must have come either this or that. But if you have no way of knowing, no way of telling, even in principle, that which way it came, that is what it means by the photon paths are indistinguishable, then you will see interference. But if there is a way, if there is any way, even in principle, that we can figure out by detecting photon here, we can figure out whether it came this way or that way, interference will not happen. Interference will actually occur. So that is the quantum indistinguishability. So as long as you have no way of telling which way the photon comes in an interferometer, then you will see the interference. The moment you have a way of finding out, even in principle, the interference is gone. So that is what we'll actually kind of show you. And that indistinguishability, distinguishability argument, we will try to address through the polarization of light. Okay. Light or a photon is like a field, so you can vibrate like that, its amplitude can do like that as a vertical polarization, or it does like that. That's the horizontal polarization. So light can have two separate polarizations. So here my laser is producing vertical polarization. So this photon is vertical polarization. Whether it goes this way or it goes that way, it has a vertical polarization. Okay. Now in this situation, if I detect a photon at the camera, I really have no way of telling which way it came. And in this case, I have these photon paths are indistinguishable, hence I will see interference. But let's start the experiment again, but this time I am putting what's called a half wave plate. I'll actually show you half wave plate, real. But here, what a half wave plate does, it just rotates the polarization of the photon. So if it's vertical, it will actually make it horizontal. That is the role of that device. So that means this vertical becomes horizontal. But if the photon actually went this way, it will remain vertical. So photon has to make a choice whether it goes this way, that way. If it goes this way, it will eventually become horizontal before this beam splitter. If it goes that way, it remains vertical. So from this camera perspective, if I detect a photon with horizontal polarization here, then I know it came this way. Or if I detect a photon with vertical polarization, then I know it came this way. That means these two paths are no longer distinguishable. These are now distinguishable. So that means no interference. Fine. Now, if I can make it indistinguishable again, how do I do it? Let's put a polarizer. This is all like that. This is horizontal, this is vertical, but here I am putting a polarizer. Now, what is a polarizer? What does a polarizer do? The polarizer selects a particular polarization direction. So, if I have a polarizer at 45 degrees, and if I have vertical polarization right, then it will just select this component, this cosine theta. That factor will actually just let pass through. So whatever goes through the polarizer actually becomes only the 45. If the polarizer is 45 degree, only the 45 degree polarized component of any light field will be able to kind of pass through. So this is horizontal, this is vertical, this has a component in the 45 direction, this has a component in the 45 direction. So now, this from this side it's also 45, this side is also 45. So now if I'm detecting a photon with the camera, it is 45 degree polarized, and now I have no way of knowing whether it came this way or came that. So although they were distinguishable here, by putting the polarizer here, I make them indistinguishable again. So in this case, the photon paths are not indistinguishable. Right? That means they are indistinguishable, and the fringes will be dark. Okay. So this thing that even though they were actually distinguishable, I have the possibility of erasing, right? Erasing that information. I can erase the possibility of distinguishing them, and if I can erase, then I can make that part not indistinguishable, that is indistinguishable. And this is also called a quantum eraser. You're erasing the possibility of distinguishing them, and that makes them indistinguishable, and then you can see the interference. Again, there are a lot of applications for this entire quantum technology and so on, but again, we will not go there. We'll just show you a few kind of things. And this thing actually is the basis of wave-particle duality, which actually will try to. These three concepts that we are doing, they are not completely separate. They are kind of intertwined, just different ways of putting maybe the same quantum weirdness. So things are kind of related. So this is the kind of very basis of what's called the wave-particle duality. What is the wave-particle duality? As kind of Aditya was saying, it is the way things are. If regarding light, if you ask the question whether light is a wave or a light is a particle, in fact, this question was asked by Newton. It's that code. In his time, light was particle. Then after 100 years, light became wave. Then after another 100 years, light became everything. So now in 2023, it is all confusing whether light is a wave, light is a particle. So what we understand, light is both wave and particle at the same time. That is the best description. Although this is as nonsensical as it gets, but it is the best description. So this is the wave-particle duality. Now, the last thing we'll show is the single photon interference. So we can show you single photon interference even at the Mars interval, but there is some difficulty, at least in this environment. So when you do it in the interferometer, you are more familiar with. So this is a very simple thing, the light source, screen with a slit, or you will get some pattern over this. Another slit, some pattern over there. Put both slits, you get some kind of pattern. So how many of you have seen Young's double slit interference? Just get an idea, for example. So now this is the interference of dark bright that you actually get. And the way you explain is exactly the same. This is classical way. That of course the light comes here, you divide the amplitude, that also means division of energy. You add those two amplitude, that is the superposition of amplitude, and you get the interference. Fantastic. Now, question. If you have this Young's double slit and this light source, I get this nice pattern. What if I reduce the intensity of this light source? I'm just dimming this light source. Then what happens? Then the pattern remains the same. It's just that the overall intensity will reduce, but the pattern remains exactly the same. Next question. What if I reduce the intensity even further? Any guess? The pattern remains the same. Only the visibility becomes pretty poor. Maybe from there you are probably seeing it as a dark thing, but there is some pattern over there. Let me continue another question. What if I reduce the intensity even further? Any guess? Same thing? Like reduce intensity, the same pattern. This is what you see. If you reduce the intensity even further, this is exactly what you see. So these are now dotted structure. There is no longer continuous intensity pattern that I see. But of course, if I am not able to see here, how come I am able to see here? Because here I had a cheap camera, now a very expensive camera. But with that expensive camera, what I see is that these are no longer continuous distribution of intensity or energy. These are packets. Right? If I reduce the intensity even further, then the number of dots will just reduce. Okay? So through classical theory, we can actually explain up to this point. But this intensity pattern becoming dot structure, you simply cannot explain using the classical theory. So up to this point, quantum classical, everything works. But beyond this, you have to have quantum. Now this fact that you get this dot structure, it is not necessarily only in the context of interference. Even if you have just single slit, and if you ask the question, reduce the intensity, fine. Reduce the intensity, that. Reduce the intensity. What do you see this time? You can, yes. And reduce intensity further, this is Q naught. Okay. So this is the wave particle duality that here you see that the interference is happening. Here you also see sorry, should go to the other one. Here you see that the interference is happening. Here also, although you see this is a dotted structure, but you see the semblance of kind of dark and bright areas. And if you collect enough dots, then you will actually have a continuous pattern. So you do have the interference there, but you also see the particle interior, right? So this is the that light. What light is? It is particle and wave at the same time. Now, when you think of particle, what do you think of? It is something localized somewhere. When you think of wave, what do you think of? It is delocalized. So quantum theory says light is localized and delocalized at the same time. So something is somewhere and everywhere at the same time. This is as nonsensical as it gets, but this is the best explanation. Does this make sense? No. Is it true? Yes. So that's all.
Question.
Yes.
So you are decreasing the intensity by changing the distance of the string.
No. I am putting it's an absorber.
Absorbing.
That it absorbs 90%, then I got 99%, then I got 99.9999%. That is a little bit kind of comes out. So that's because I have cheaper source, but if I have more money, then I can go truly single photon source, in which I put a click, one photon, click, one photon. So those sources are also available, right? Yeah, but again, any question, please do ask. Okay, yeah.
Sounds fascinating, of course, but it's worth thinking deeper at the quantum level how our universe works, right? So it's not clear to me with respect to the result that you just showed me. With respect to the result that you, I'm not sure if it's working. So in the second case that you just showed, Young's double slit experiment, it was single photons that were detected. Okay, so there is a probability pattern, of course, I understand, that at the end you're having a localized event. But it did not seem in your previous case, whatever the fancy name of the interferometer was, that there were single photons detected. It was like a pattern or something. So what kind of interference were you talking about in that case? Was it also single photons that are detected like this and there is a probability pattern, or is there actually something like a distribution, uniform distribution of intensity somehow where the energy gets smeared out or something like that?
Okay, very good question. So you're right. So the question is, what was I doing in the other Mark Zender interferometer, and what am I doing now? So at the high light level, which I was showing earlier, that is the level where I was seeing a pattern like this, even in the Mark Zender interferometer. Now, as I said, if I have what's not here, but if I have more sophisticated environment, then one can actually see this kind of situation even with that interferometer. But that is not possible in this kind of setup. So we are choosing this setup, which is that can be demonstrated with this. So here also, if you are high light level, you can again get this kind of high light level intensity pattern, which you can in fact interpret as a probability distribution, intensity distribution in the classical way, no sure. But the classical way of thinking actually breaks down from this point on. This cannot be explained with that kind of intuition. So then this just because that one is difficult, this one we are actually showing, but it is exactly the same in the field and example. And of course you don't believe me 100% anymore. So we'll show you that this actually happens like that. That's what you have to prepare for.
Anand, you can also code Dirac.
Question.
So
just that timely that we actually code Dirac, and so
one question here.
right.
So, do you have an actual single photon interference, and you just let one single photon go, and you see a
Yes.
interference?
Yes. I like that you display at this point. So we want to build up on this beat, and then we'll show you by one, and by one. Then we'll build up a pattern. So that
Okay, build up a pattern is a different thing. Single photon, you stop your experiment, you look at the pattern, and can you see the pattern?
Yeah, yeah.
Yes.
After you stop, after a single photon,
Yes,
no
that's,
other photon involved.
That is correct.
that is why 50 lakhs.
So the eyes actually are single photon detector. Human eyes are actually single photon detector, but I cannot put anybody there. So that's why the camera is the expensive one that can actually do single photon, and then we show single photon, and then we show the pattern.
So that is why you do have a click photon source with your
No.
I don't have that much money, so this is like it's one by one, but it's not like on demand whenever I want. But it's like one by one in the sense that whatever is the collection time of my camera, within that I have only one person.
so the way of making it a single photon source is by having a higher resolution.
We are picking.
By increasing the resolution of the camera.
No. To see a single photon source, you need a single photon measuring device. Either you can put your eye in that path, or you can put in atom by atom kind of detector. It just detects h bar omega energy and not more. That is what you want. Fine? So this is good that you're not believing at this point. Alright, so just to summarize, how do we understand through the classical wave theory that you divide the amplitude into interference, that means division of energy, and but this is fundamentally incorrect. It works at high light level, but it is fundamentally incorrect because it doesn't work at single photon level. Quantum mechanically, what we have is division of wave function. We don't have amplitude anymore. This is wave function. This does not mean division of energy because we cannot, and thereby you actually expect interference. This is fundamentally correct, but since the math is little involved, so you typically use it only at few photon level. If the high light level is there, you don't use this. But it doesn't mean that the quantum is not true at high level. Quantum is true at every level, but you typically use it only at single photon level. The classical one, it works at high light level, but it's fundamentally incorrect because it doesn't work at single photon level. And all this again can be summarized as Arsa was saying. How do you explain this and all that we have shown? This was very nicely by Dirac. Summarize, each photon interferes only with itself. Interference between two different photons can never occur. What does it mean, each photon interfering with itself? I have no idea. So, again, does this make sense? No. Is it true? Yes. Okay, so at this point, we will stop the PowerPoint presentation. Now we'll actually go there and show you. This is a setup of the first experiment, the Mach little phenomenon that we are actually seeing. And we should come here.
The question.
Yeah.
So why did you use 3 mirrors as well?
Sorry.
3 mirrors versus 1. Why?
3 mirrors versus 1. Okay. So if you are a theorist, you can do 1 mirror, no issue. But if you are an experimentalist, you find it one very difficult. So you may use 3 mirrors. I am an experimentalist, but I am doing a presentation only 3. If I am an experimentalist, if I am actually doing experiments, I will actually build more. So, but the point is, you introduce more only as to see what is feasible to do. So experimentally, what is feasible. But the point is, so here the thing is that it's easier to align with 3 mirrors. And second, if I want to introduce a path length difference between this and that way I can do by moving these 2 mirrors together. Okay? I'll show you. The real setup is slightly more complicated than this, but this is where we are.
Sir, any reason to the beam is being widened?
Beam is being
Widened.
well. If it's too narrow, you can't resolve your resolution. You can't resolve the fringes. So to be able to see the fringes, you have to kind of make it wide.
But in theory, it shouldn't matter, right?
It should not matter. If you can resolve, fine, but typically most of us cannot resolve because we have to see it's magnified, and that's why it's magnified. That's only reason.
Should we use the right angle prisms for the refraction AIR in case of the mirrors, or we use the normal very costly mirrors, polished mirrors?
Either way it works. Either as long as
earlier diagram you have shown the right angle prisms.
Yes. Yeah. So if everything works, as long as it reflects, it doesn't even need to be 100%. Even if it says 90%, 90%, of course 10% is lost, but I will still some interference. I will not see the best quality interference, but I will see at least something, whatever there is. So that is first. Okay, so now this is the setup that you are actually seeing. Here, this is the laser, which is what I was showing. Radhika, you need to just go a little bit inside out. Yeah. So now here you have this steady there. Just it goes here with this mirror. This is another mirror, and this is my first lens that I'm putting here, and this is the second lens that I'm putting here. This is to expand the beam. After that, it falls under this beam splitter here. Okay. Now this beam splitter splits the beam, goes this way, goes that way. Maybe it's hard to see, but there's one mirror there, it goes there. And then from here to one mirror there, and then it goes there. So that's the second beam splitter where it actually combines, and then it goes into my detector. That is my camera. Okay. So this is the exact same setup that we actually have. Now we will be putting this half-wave plate and quarter-wave plate for our quantum eraser experiment. So first, I just want to show you what is. How many of you know how does the polarizer? Okay, can you see a beam of light? It's maybe a little elliptical because my beam is coming like this. You have the camera. Election. Can you handle that? Okay, this one. Right. So what I want to show you is just a light beam coming from if you can see, that's my laser beam. I mean, I'm reflecting everywhere, and the laser beam which is placing like this path. Okay. So that's my beam. If you see it here, it's a little elliptical. That because I'm not projecting it. If I do a projection like that, it becomes circular, but that I cannot see. That's why I have it like this. Okay. Now this is a polarizer. This device is a polarizer. Now if I put this in, now what a polarizer does, this light, the red light that actually was incoming, it is vertically polarized. So this polarizer will actually select just the projection of it. So wherever the polarizer, I don't know where it is. So I'll just change the polarizer and the direction. You will see the intensity decreasing. Because the electric field is like this, and the polarizer is a theta, the projection will be E cosine theta, and the intensity will go as E square cosine square. So whatever the intensity, I'll change by cosine square. So let me just rotate this polarizer and you see the intensity decreasing. You can see here, not with the screen, but it is much easier seeing here. So you see, the intensity goes to minimum, and if I keep doing it, increases. Because the cosine square theta 0 to 90, 90 to 180, then it will actually come back and go again to 0. So if it's a vertically polarized light, and this is the minimum, why is it not going to 0? Because cosine 90 should be 0, so intensity should be 0. Because this is slightly cheaper polarizer. So if you have more money, you can buy a more sophisticated one in which there is no leakage. So this is a real experiment. So I mean, if you want, this is like 99% kind of extinguishing ratio. That 1% is what you are actually seeing. Put more money, you can get 99.99, but 100% infinite money you have to actually put. But this is what you see as the kind of intensity. Okay. Now, what is a half-wave plate? So this one is actually half-wave plate. But from here you can see, you can hardly see any difference. But once I put this in, half-wave plate is a device that rotates the polarization. It doesn't select; it rotates the polarization. So for this one, if I rotate, doesn't matter. It just rotates the polarization, but intensity remains the same. Okay, you see, there's no change in intensity. Okay, now watch. So let's put the polarizer at the minimum, that means this one was, incoming thing was a vertical polarization, and now what's hitting this polarizer is at 90 degree. Polarizer is oriented 90 degree to what was the polarization here. Okay? But now if I insert the half wave plate in between, this thing can actually rotate the polarization, and if it does rotate, then it can actually rotate to the extent that the polarization of this thing gets aligned to this. So now if I rotate the half wave plate, you see it will actually change the intensity. So whenever it is rotating in such a way that it actually aligns with the direction of the polarizer, you see the maximum intensity. When it goes orthogonal, then you see the minimum intensity. So this is how a polarizer and a half wave plate works. Half wave plate rotates the polarization. Polarizer selects and projects the polarization. Right? Okay. So with that, now we come back to this interferometer. Can you go up? Maybe you can. Don't fall.
So in all these cases, energy is not changing, only intensity is changing.
Yes. So you think in terms of photon energy?
Total energy, wave energy or photon energy, what energy or amplitude we are talking?
Well, if you say in terms of the intensity, that intensity goes as cosine squared theta, and that of course is in. But when we come to photon, then I mean, if just a one photon comes to a polarizer, then what happens? That is probably your question, right? If only the h bar omega energy comes in, and if I have polarizer oriented at 45 degree, then do I get h bar omega by 2? Because cosine squared theta is, cosine squared 1 over 2, so 1 over 2. So does it get divided? Again, we can't divide the photon. So the way it will manifest, that if you actually do this kind of experiment with polarizer at 45 degree and physical photon coming vertical, and if you do that experiment 5,000 times, then 2,500 times you will actually get the photon, 2,500 you will not get. So that's how it actually manifests. Cosine squared theta.
I can just tell them that intensity is independent, number of photons. That they don't.
Yes. So is that fine or fine? So okay, so this is the role of the polarizer and the half wave plate. So now we are at the so right, fine. So now you have to you have this interferometer. Meenakshi, can you go to the just change to good slide? Right. Go before this. After, no, after. Go back without the half a plate. Slow. Go one more back. Stay there. Okay, so this is the experiment that we have. Okay, just a vertical polarization photon coming in, and there's no way of kind of distinguishing it. And now this time I will expect the interference to happen. Just click one more step. Click. No, without the half plate. Go back. Yeah. So this time we'll actually expect the interference to actually happen. So this is the experiment, and then what we are detecting in this camera here, right? This we are projecting onto this computer screen, and now we will show you what happens on the computer screen. So what you are seeing now is what we see on the camera. So what you are seeing now is what we see on the scanner. Turn off the light. So you see the things are moving because this is real time. In fact, if you don't believe me, then if I block one of the things, the interference will actually be gone. See that? You still see some light because the other one is still working. If I remove it, you see it. So
what is new here? What is frequency and what is the rate at which photon
new and what is the rate at which photon will come? So the frequency of this laser, the wavelength is 633 nanometer. And the rate at which this photon is infinite. Right now it's very highlight here. So number of photons are literally infinite here. We will go to one photon later, but at this point it's a little infinite. So this is my setup there. This is what I'm seeing on this camera screen. And you see, of course, things are fluctuating because this is a real setup. There's a these two are on the interferometer. Even if you have a slight diffractive index difference, you will see things are kind of changing. So I see nice interference pattern over there. Now, can you go to the slide? Right. So move on. No. Keep that. Fine. Yes. Right. Now I'm putting half-wave plate. One more plate. And then expectation is, since I put a half-wave plate here, this makes it distinguishable and the interference will actually go away. So let me insert the half-wave plate. Let me insert the half-wave plate here. Everything else is exactly the same. Go to the right. Keep it there. Slide it. Right. Since you may or may not believe me, you'll do real time. Interference. I'm just inserting this half-wave plate, which will make it distinguishable, and the interference is gone. Okay? I'm just tighten it. Okay? Now the interference is actually gone. Now next, as I said, keep it here. Now, no, don't change it this time. Now we will do a polarizer, which is what I was kind of showing. Now if you put a polarizer, then that should get the interference back because it is erasing the possibility of distinguishing the two photons. I need to make sure it's 45 degree. Okay. So now I have a polarizer at 45 degree. So you have no fringes, and I just put this polarizer over here. The interference is back. Okay. So we have just erased the possibility of distinguishing erase the possibility of finding out which way the photon comes, and the interference is back. You would say it is back, but the quality is not very good. I will say yes, and what is the reason? Money again. So my polarizer is not that expensive, and hence you see little distortion. But the interference is there. If you use better polarizer, then you can get as nice a visibility as you see actually started there.
Maybe you can remind that the polarizer is kept after the second beam splitter.
Okay, so what Aditya is saying that we need to remind that what has happened now is that this was the half-wave plate and then no interference, and then we are putting the polarizer. So here at this beam splitter, they are already, you could actually distinguish them, but now that we are putting the polarizer after the second beam splitter, right before the detector. So even right before the detector, if I have a way of erasing the possibility of distinguishing them, the interference actually comes back. And that is the idea of quantum eraser. Question? Yes.
So if every photon interferes with itself only, why does it even matter that two photons are distinguishable?
No. We have not talked anywhere about the two photon indistinguishability. Thanks for the question. So we are not talking about the indistinguishability. We are not saying this photon is indistinguishable from that one. No. We are only talking one by one. So when the photon goes this way and when the photon goes this way, these two possibilities, if they are indistinguishable, that is what we are talking about. Fine? So sitting at this camera, if I can figure out whether the photon came this way or came that way, then I will call the paths are distinguishable. If I cannot figure out which way they came sitting at the camera, then the paths are indistinguishable. If the paths are indistinguishable, interference will happen. If the paths are not indistinguishable, interference will not happen. If you bring in this two photon aspect, that is also there. And then the quantum mechanics gets even weird, right? Two photons. And then you have all this thing called entanglement and so on. The last year's Nobel Prize was given actually for that. Just for that weirdness that people have actually proved that yes, that weirdness does exist. So what I'm showing you is the level 1 weirdness, there is a level 2 weirdness. So
second content.
Yes.
So only one question here. You are passing a beam. You are not working with one photon.
No, exactly. So again, that's a discrete. Thank you. So we are not doing one photon yet. We will do it. So right now it's just a problem.
So what you are doing is true for classical electromagnetism.
Yes.
That absolutely correct. Absolutely correct. So right now, whatever we have done can be explained classically, can be explained quantumically. No issue. What we'll show next, there classically will fail. But right now, everything is good. We done classically as well as quantumically. Okay. So before we go to the next step, there's something, maybe a few fun things we want to do.
Can we do? Yeah, see that.
So what I want to kind of show while Suman is setting up is, so you see this. See, this interference happens because there's an angle between these two, right? And then we have seen the interference actually happening. But what if we change the angle between the two? What if we reduce the angle? Yes.
As you said, state that you take a single photon, and when the single photon is contact with the beam splitter, so why it is separate in two terms? So there is a phase difference between the phase difference. That's why it separates. So if you say that you use a single photon, so why it is separate? The phase difference.
So she is asking why does it separate? The answer is it does not. Well, if it is single photon, it does not separate because it cannot. If it's a beam of light, of course you see it is splitting into two, it is separating into two, and what you are saying, the phase difference idea, everything works there. But when we go to single photon level, which I have not yet, we are building up the discrete, so that's what I like. So when we go to single photon level, it cannot go both ways. It doesn't separate. It goes either this way or goes that way.
Sir, my question is that how
How? Nobody knows. So that's how it is. But how? Don't ask. This is how it is.
No, I think she's asking why the separation happens. I think half silvered mirror or that.
Oh, is that what you're asking? Oh, that's
How
a
does it
okay. So this is a, if you're asking why, so this is a device. This reflects 50% and transmits 50%. Like mirror is a device that reflects about 100%. But
the second beam is translated totally.
right.
So sir, there is a phase difference, no sir?
Yes, phase difference is there. Yes.
So sir, अगर phase difference from the R आए, तो sir ले तो आप एक single photon ही रहता है.
Right.
So how is it?
हाँ, तो वही तो
How the phase difference occurs?
How phase difference happens? See, phase difference. Okay, so you're saying the phase difference between the light that goes through this and through that. Is that what you're saying? Right? So phase difference occurs because light travels, let's say, different distances in this one and in that one. That is one way. The second way that we have done is that there is a little tilt between the light coming from two different directions, and that's why the phase difference occurs. That's what we see in the interference pattern. Because it's little tilt, the phase difference occurs as a function of the vertical direction, and that's how we see the interference. Now, if I reduce the angle between the two, if I reduce the angle between these two beams, then the way the phase changes, phase difference occurs will be different. And now you see the intensity, the interference pattern will actually change. We will increase the separation between the phases or decrease them, which is what I will show you next. Fine? Any other questions? Yes. Sorry. Alternating the camera. Sorry, your microphone.
How can we attenuate the light beam to a single photon?
Sorry, can you repeat the question?
How can we attenuate the beam to a single photon to pass
How can you attenuate?
the beam to a single photon?
Well, there's something called neutral density filters, which can attenuate the light to a factor of 10 or something. And if you put enough number of them, then you can reduce, the thing to come to the level that only H or omega is coming from a snare. Right? Yes.
Yeah, so change the angle of polarization distribution for
That's right.
So can we change the angle of the polarization a little bit and still can expect for the intervals?
Yes, but you should have asked me this question 5 minutes ago. Now we are set up for some. Yeah, I could have changed the angle of the polarizer, and then you will see if it is at 45. A very good question. If it is 45, Then one is equal contribution from both H and B, cosine square 45, cosine square 45, right? So that's why you see these high contrast fringes. But if I have a polarizer at some other angle, not at 45, then you get cosine square, it's a 60 degree, sine square 60 degree, which are not half. In that case, the contrast of the fringe will actually decrease. Okay, so that, and so it's like to the extent you are now introducing the indistinguishability. With 45, it is perfectly indistinguishable. Right? So next, what I want to show is that we want to change the angle between the two beams, and I want to show you what happens. Okay. Okay, so
I maybe means you wanted quantum. This is completely dark. It is happening. Okay, fine.
okay, now what you see here, this is what we are seeing in the camera. Okay. Now you see something fluctuating pretty badly, right? So this is the situation where those fringes have kind of become just one. Can you just show real time? A few fringes and then. See the fringes, and if I change the angle, we can increase the separation between the fringes, and to the extent that becomes a single block. It is very hard to do. It looks at this kind of environment, but it is actually possible. Okay. Now you see the intensity actually is very low. It is actually fluctuating and sometimes goes away, sometimes very intense. You know why is that happening? So first of all, you see this just a kind of a blob. So if the intensity is, if I have my laser on, but at the camera, I sometimes see no intensity, sometimes see more intensity. So when I see no intensity, where does the intensity go? Because intensity should be conserved, energy should be conserved. So when this is changing with no intensity, where does the intensity go? Energy should be conserved, right? And energy is conserved, and what is happening in this case is that the energy goes here, right? And so what we will do now is get that beam also into the camera. So that is the second beam. Okay. So these are the two ports of that Mark's interferometer. Now you see this complementarity whenever this is bright, this is dark, bright, this is bright. You may be asking, maybe you are showing me something nonsensical, but let me just close one path. So one path in interferometer I am just closing. Everything is stable. Because now it's just a 50-50 split, no issue. Okay, so no problem with the experiment. But the moment I remove it, if I moment I let the light come through the other one as well, now interference happens. Interference happens, it will shake. Because to make it stable, this is actually very high in research problem as to how you make it stable. Okay, in fact, this is so unstable that if this is already changing, if I clap it, it will actually do more. Well, you can't even really make it. Or if I blow some air, it will actually do more. See that? Now, as somebody is saying, why did you put two extra mirrors when one was enough? This was to kind of introduce some separation, and that separation changes the phase difference. That phase difference will actually make these fringes go bright and dark. So here is my this stage where I can push back the set of two mirrors, and if I actually do that, this is actually shaking already so much. But let me just do that.
Okay, let me just a minute, Anand. Now response will be more.
So now see, this is more regular because I'm actually introducing the very fast, right? So it is a good thing or a bad thing that this thing fluctuating so much. Is this a good thing or a bad thing? Is actually a good thing in the sense that this situation, this camera, what we are seeing, this is so much sensitive to what's going on here, right? If there is a little refractive index fluctuation in the path of the photon, you can actually detect it. So this is a very good detector. This interferometer is an actually extremely good detector for detecting phase fluctuations and those kinds. Again, a lot of application, but we will not do it. But this is what I wanted to show. This is not happening just because we have not aligned it. If you block it, stable intensity, Remove it, you will have the fluctuation. Fine?
Sir,
Yes.
regarding that total intensity measurement there, does it have any significance in the when we look at it? That the measurement that's showing up on the right side.
Yes. No, this is just to show that the energy is conserved. So if let's say when you have interference, you have bright dark, bright dark, bright dark. So there is never a situation where it is nothing. But we have aligned the interferometer so well here that there is no intensity. Now there is no intensity. Then the question is, where does it go? The answer is it goes to the other port, and that's why we are actually showing that it actually goes. And if you add these two, the intensity remains constant as to whatever was intended. Right? Now at this point, we will go to the other experiment, that is the Young's double slit experiment. But before we did that, I wanted to kind of do an experiment with everybody.
One question.
Yes, yes.
So this the light intensity is fluctuating between the two detectors. Is there a time period involved, or how does it relate to the either the frequency or the rate of photons which are coming in? Is there any correlation with that?
Yes. So it is basically the fluctuation is proportional to the phase difference between the two arms. So you have this, if you travel resistance T1, travel resistance T2 through this. So that's omega T1 minus T2 will be the phase difference. Now that T1, that can change because maybe the refractive index is kind of changing that air a little bit because maybe it's hotter, over here and not so hot over here. That teeny tiny bit temperature changes between this arm and that arm, that can also be detected through that fluctuation. So that fluctuation actually makes it a very, very sensitive detector, and there's lots of uses for that. Okay. So next, actually, we want to go to the Young's double slit and show you the fun stuff, because we have built enough questions on whether the single photon happens or not. But just to make it fun, we'll do some. We want you to also get involved in this experiment wherever you are sitting. So we want to show you Young's double slit experiment wherever you are sitting in the real time. So what I want is everybody pluck a hair, those who have it. If not, you can borrow from your neighbor, right? Okay, so what we want, especially fine with this light, just get one hair stand, and what you need to do is just your eyeball, just need to get your hair stand and just go like that for your eye. But don't look at the hair stand, you look at the source, my LED of this phone camera. And then you will see as you are kind of moving across with this hair, you will actually see nice interference happen. Those who are further away, they will see better interference. Those who are near, they will have a little hard time, but you will still see it. Okay, so all you need to do is have that hair and just move it across your eyes. But don't look at the hair, look at the source. And with that, since the hair splits this light into two, you will see interference with that. So just let's try it first. Look at the source, but move the hair. Keep the hair very close to your eyes.
Oh, I did not realize.
You might see the multi-color interference pattern.
How many of you saw?
You can get a hair from your neighbor to your direct.
Just to look at the hair. Then you look at the.
Anybody sees anything?
Look at the.
Yes, excellent. Who has seen the color?
Keep it close.
Oh, excellent. I think those who are far, they see the things that are separated. So you have just performed just one experiment yourself. And if you actually believe, your eyes are seeing the photon sensitive, so you actually have direct or see the photon sensitive, but you cannot prove it, but you have. Okay, so now to show
Stick your
what
hand here. Catch it. Just take it.
okay. Last 10 seconds.
Exactly. Got it? But keep it stable against your eye. Then you move the eye.
Alright. So we will now go to the So now you change that. Now we will change the. Now we will change and go to the Young's experiment. So I think I can quickly. Now we can have the light from this sun. Right. So this is an experiment. You can put it in hand. Okay, so here I will not spend too much time because I have already shown you. Again, this is a separate setup. This is a laser. Again, few mirrors reflects. It comes to this device. This device is what's called spatial light modulator. You don't need to know anything about it. This actually is my double slit. It's a very expensive double. I do have money to buy, some expensive stuff as well. So here we have very expensive double slit, and then from that light comes like this, and then gets onto this piece, which is my single photon camera. Of course, you see this one. This is just a cardboard pipe thing. This is not very expensive. But this is there. You do all this jugaad for this doing these kind of experiments. This is there to protect my camera. Okay. So this is actually a single photon camera. Very expensive piece, but it can detect single photon. So what we will do Young's double slit experiment. Now, if you see here, Radhika, can you show this neutral density filter? So there's a lot of things you see here. This is just to attenuate the light to the extent that there's no light at all. To the extent that you can actually see it. If you don't believe, you see. If I do it here, you can see you can see some light here. Radhika, can you focus here on this? You see some light here, but if I put it after this, you can't really see any light. Right? So this is the neutral density filter, those who were asking. So it almost attenuates, but it doesn't mean there is no light. It is so low that it is at the level of single photon. So you and I cannot see, but this camera actually can see. We already have a double slit on this, and then we'll show you that photon by photon, and then we'll have the interference pattern.
So,
yes?
So like a normal single photon sources, can we calculate G2 and other things of this?
Yes.
So what's the G2 of this?
G2 we will not talk, because that's for this is level 1 only, so only one photon. What is talking about G2, that goes to a 2 photon level, that is the quantum weirdness level 2. So that may be for some other time, but now just 1 photon.
It's a laser device, so G2 is 1.
It's coded.
Yes. Alright, so this is again the setup. Now we will go to what we are seeing on the this EMCCD camera screen. So what you are seeing is the EMCCD camera screen. What this is that double slit. You see this slit has this thickness. This is the separation, and this is my camera screen that I'm seeing. So these dots that I are seeing that are actually single photon, but it starts fresh. Let's refresh. So we are starting. So now this dot that you just seen is actually a single photon. Why did it? Fine. Okay, so you just refresh. Okay, so now we are starting now. So that's a single photon, only one photon. The second one comes in. So this attenuation is so much that the rate is so
So,
big.
Anand, how are you producing one photon?
I am producing one photon by attenuating.
You walked out.
No, I did not let him walk out.
He walked out and came back. Neutral density filter.
I kind of. So the same laser. Maybe Radhika can. Okay, so that's a laser I have, and here I am putting a lot of. Can we maybe turn on the light one more time? Right. So
how can I know you are not cheating? You are saying you are one photon. How can I?
That is, you have to believe, or you have to come to my lab, spend 6 months, then I can make it. But right now, some sort of faith needs to be. Otherwise,
Neutral density filter, it exponentially cuts down the light at the end. You can't see. I can show you that.
yes, but then again, if you
not
don't
okay.
yes,
I understand.
so it comes, there are what he was talking about the G2 and so on. So there are ways in which you can actually see things are coming at single photon or not and so on. So the way you can actually see is that I have only one dot on my camera, and this is a pixelated device. This camera is a pixelated device, and each pixel, again you have to believe me on that. Each pixel is capable of detecting one photon. Once it gets a pixel, then it is dead for a time. It cannot get any other photon. And then you have one photon worth energy coming over this area. So since one pixel is getting hit, then that means this entire energy actually comes and falls into that pixel. So just one pixel actually gets So it doesn't have enough energy that can make all the pixels. There are 250,000 pixels here. All the pixels, just one goes lit. And for that pixel to go lit, it requires a photon energy. That is the requirement. Okay. So with that, let's start again. So maybe someone start again. So this is the double slit, and again, now that we have slightly better faith on this, a single photon coming in one by one. So it goes to the double slit, so it means the photon either goes to this slit or that slit, because it did not split itself, and then falls onto the detector. And then we are seeing the detector, it actually falls one by one. So what you are seeing actually are the single photons. What is the size of the single photon? Size of the single photon is the size of the pixel, which is about 16 micron by 16 micron. Okay. So I mean, these are again, it's a very complicated technology as to how these detectors work, but it is the way it is. That 16 micron by 16 micron piece goes lit the moment we have h bar omega energy falling on it, and then it is dead for a minute. Okay. So you have these photons falling one by one, and it is completely random. Okay. So we can keep watching this, but at least only thing I want to convey that this is such a boring random pattern, right? But in Young's double slit interference, we expect some pattern, some nice interference pattern. So where is that pattern? The entire energy comes here, then entire energy comes here, then it comes here, maybe comes somewhere else now. But there is no pattern here. So what does that mean? How do you explain it? You cannot. This division of amplitude going to division of energy, and then division of amplitude implying division of energy, then combining giving interference does not work here. It was working at the level of that at highlighter, but at this level it simply doesn't work. All I'm seeing is a single photon falling one by one. But now if I increase so if you actually want to see this pattern build up, you will probably have to wait at this rate at least few hours. After a few hours, you will actually see some pattern. But even if you wait, maybe I don't know if you can see, there's more here. I mean, vertical wise, I'm just giving you some hint. There's more here, there's more here, more here. But there's less here, less here, less here, and so on. But it is still quite random. So let's see if I can increase the speed so that you can see some. Now, so I have just reduced that intensity, just a little bit, and so you see there's more photons kind of coming in, right? So there's more photons, but it is one by one. That is the whole point that I wanted to show. That this is what we have here is that photons going through this double slit, through this or through that, and then falling on the detector, and you see them only one by one. And now you can see maybe a little bit. There's a more build up here than over there. More build up here than over there, and so on. And if I now at this point, since we don't have maybe that much, maybe if anybody's question, let this build up. If there's any question, I can maybe take up the question. Then,
So
yes.
These histories, you restart the thing again. Then it starts with a single photon again. Now, how it retains the history and how it erases the.
Fantastic question. So the point is, well, I'm sending photon one by one, fantastic, and it hits the double slit and then falls into my state. Then the first one hits here, second one hits here, third one hits here. Do they have any way of communicating between them? Okay, you fell there, so I will fall there because we have to build up an interface back. Answer is no. It is completely independent. The first one has no idea what the other one did. So that's why we are doing such a slow level. In fact, I can reduce the intensity of the laser so much that I have only one photon in one day. And if we wait for maybe light year, then I will get exactly the same pattern. So there is no history between the photons. So
in the display there is a history. You're just keeping track.
In the display there is a history in the sense that I'm just, if it falls here, I'm just keeping. In fact, you have that other screen where it is just one by.
Oh, that is.
Fine, I'll just keep that. So we have that. If you this is my frame by frame collection. Right? See, but this probably you see one dot up here, one dot appears there. So that is actually what is happening. Okay, so just one by one, each one second you get. But come down. Okay. But what we do in this here, this is accumulation. And wherever it is, we're just keeping it. So this is just we are keeping it, and now maybe you can see some interference pattern happening. We can give it a few more minutes, maybe I can take one more question. Yes.
We are doing the experiment in light, not in a dark room. Does it change the outcome of the experiment that we are doing here?
Of course, of course. But we are taking a lot of care, which are not kind of given detail, that this we have a lot of ways to kind of avoid the ambient light and collect only the light because there's a frequency. That light has a frequency, this light is also changing. But if I do this experiment here, let's say if I do it in my lab or dark, the quality of the interference will be very, very different. So, but here it is to the extent that at least I can see the interference. But if you want to improve the quality, this actually needs to be done in a very dark room. In fact, it's much more difficult to do it in this kind of environment. You have to take a lot of care to actually do it. I mean, dark room much easier. Any other? Yes.
What does it mean that we are observing?
What does it mean?
That we are observing the photon tracing.
What does it mean that we are seeing photons?
Like if we are tracing that it is moving from this part of the photon.
No. See, the way we understand Young's double-slit interference or Mark's interference, any interference, right? You have a light source, you divide that into two. Even Young's double-slit, you have some light coming from this, some light coming from this, they both combine and give interference pattern. So what we are seeing is that in the case of photon, we cannot divide it. So the photon either goes through this or goes through that, only one by one. So then the question is, what interferes with what? The other question that was there, that maybe the first photon knows what the second one is going to do and the third one is going to do so on, and then they can decide, okay, you fall there, I will go there, you then go there, and then you will build a interference pattern. There's nothing like that. So this is as weird as it gets, that there's no division of anything. The photon goes either to this link or that, and that's why we are actually showing it. The entire thing goes here and the entire thing gets rejected. But now if you wait for enough time, without any history, without anything talking, what's happening with each other, you can actually see this vertical lines. And that is the interference pattern. If you wait for long, these interference patterns will actually become more and more intense. Was that fine? Question? Yes.
So the photon interface with itself to give interference better. Then why we say that we need two covalent sources to interference better?
Okay, so the question is, if photon interferes with itself, then why do we require about the coherence of the photons and so on? I mean, that will be a little advanced question for this demo, because for photons to kind of interfere, that is the basic philosophy, basic concept as to how we explain the photon interferes with itself. But that is that it interferes with itself. But how it can interfere, when it can interfere, there are conditions. And the coherence is one of the conditions, and so that has to be satisfied for it can actually interfere. Is that right?
So proceed here.
That connection. So okay, so there are.
The connection to the sea require coherence. Otherwise, it is not sea.
So it's like to see interference, you have to divide and then combine, right? And that is one first requirement to actually see the interference. The second requirement for seeing interference is that these two things that you divide need to be coherent with respect to each other. What we are assuming here, the two things that we divide, they are fully coherent. So if I have some way of reducing the coherence, which I could have done, but we don't have time. If I have a way of reducing the amount of coherence between the two, you will see the contrast decreases. But all that I'm showing you here is these two parts being fully coherent. That is the second. Right?
Sir, in this experiment, superposition principle are followed or not? Superposition principle followed.
So in this experiment, superposition principle followed. Superposition principle is absolutely followed, but the way we interpret superposition principle in classical wave theory and quantum theory is very different. In the classical theory, we say division of amplitude means division of energy. But when it comes to quantum, there is no division of energy. That is not possible. So that's why you're taking the idea of wave function. What is the wave function? Nobody knows, but it is there. So you divide the wave function, and that is something division of which doesn't imply division of energy, and that's how we actually do it.
Sir,
Yes.
for physics theory, interpret better what how much number of photons are how much intensity?
You require a lot of photons, but I'm just waiting. But now you can see little, this vertical lines are kind of coming up. But to get what we see at high level, you literally require infinite number of photons. So at this point, if our patience is losing, what we can do, we can remove one of the filters, right? That means now it's a lot of photons, and then you'll see this, the bright dark appearing really quickly. So yeah, just we set the threshold.
This might be a little tangential.
Hang on. Just watch this. This will be very fast. It's either very slow or very fast. This is still pixelated.
No, it's okay.
See that? Now you see, this is much faster. Well, we can make it even faster. Can you make it even faster?
Another one I'll open.
It's quite fast.
Fine. Okay. So yeah. So this is the Young's level interference with the single photon. Yes. You have your question.
Yeah, this might be a little tangential, but can we observe those diffractive effects as well?
So everything you can see. So the diffraction and interference ideas that you have from classical physics, everything, the pattern-wise, everything is correct. But the only thing that you get extra from quantum mechanics is that you never have a continuous distribution of intensity. You can only think of in classical mechanics or wave theory, you can only think of a continuous distribution of intensity. With diffraction, one kind of pattern, interference, another kind of pattern. You have 2-slit diffraction, 3-slit, 5-slit, 10-slit, or you can put my face, some kind of pattern. But that pattern just doesn't come as an intensity distribution. It builds up one by one. Because when you detect a photon, even if it has the possibility of being over this area, when you detect a photon, only one pixel gets hit. And that is the idea of the particle picture of the photon. And what you are seeing here, this of course comes only when you have the wave picture of the photon. And so what you see here is both particle and wave at the same time. What you are seeing here is something being somewhere and something being everywhere at the same time. As I like to say, does it make sense? No, but is it true? Yes, that's what you see.
Another thing is that on average, if you look at the vertical distribution, it appears to be one band here, one band there. Like it appears to be in 3 bands.
Yeah.
So is there any significance to that?
Which the
On average.
This is a 2-dimensional detector. That's a screen. Okay? There's a 2-dimensional detector. Now what you see in the bottom, I don't know if you can see from the back. What you see in the bottom, this is the integrated intensity. Like all the things are being integrated. Now you see the nice difference pattern. See that? And as we collect more and more photon, it gets actually good. So this is the integrated intensity, and you see nice sinusoidal pattern that you actually
But anyway, this is not in this way also it is a many photon business.
Single photon business, yes.
No, single photon, right?
Yes, single photon.
In single photons, but you are accumulating many of them.
We are accumulating correct.
So in that sense, it is also many photon business.
No, with one photon you cannot see the interference pattern. It is there, but with one photon you only see one point of the interference pattern. So to see the whole pattern, you require to collect several to see the pattern. But every photon is producing that pattern. But when
So with one photon you means you can't have this difference of intensities in these 2 regions.
No, with one photon you can hit only one pixel. It cannot distribute. So it is still part of the interference pattern that it is capable of producing. But to see that it actually produces it, you need to collect a lot of photons to build that interference pattern. But the point is, it gets built up one by one. And there is no limit on how slow you can actually collect it and still use it.
Actually, so my question was that when
So now we can actually stop it. If anybody has anything regarding the experiment that we can show, otherwise you can stop it, turn on the light, and then you can ask questions. Is there any question about seeing the setup or something? Yes.
Oh, you want to turn off the laser. We can block the laser. Don't have to turn it off, we'll just block it.
So okay, so hang on. So if we block it, this will still be there. Okay? This will still, because this is an accumulation. But you will have no further things coming. So just refresh it. Or just refresh it, correct. So now there's nothing. Well, you might still have something because there's a light. There's an ambient light. Is that fine? Whenever you want, I can lift it. Just tell me lift it. Lift it? Okay, lift it. There it is. Fine. Any other doubt, question about the setup? Okay, so now we can turn it off and we go to the highlight level. So we can just
highlight.
No, I mean, turn on the light. Just hang on.